Good day everyone, we are the group 7 and today's video is we are going to answer the given problem and number 7 using the truth tables. Members Christine Joy Fronas, Angeline Gumapak, Chariza Tindoy, Rosalyn Sumambot and yours truly Stella Foronas. First is Angeline Gumapak.
For number 1, give the truth table for NaND P and Q. So let's first get the first column, which is P. The values of P we have true, true, false, false. Then the second column, which is Q, we have the values of true, false, true, false. In the third column, to get the values of P and Q, if P is true, then the Q is true. So the P and Q it becomes true. Then the P is true. If Q is false, then the P and Q becomes false. If P is false, then Q is true. The values of P and Q becomes false. If P is false and Q is false, then the values of P and Q becomes false. In the fourth column, which is not P and Q, so the values of not P and Q we have false, true, true, true. For number 2, show using truth tables that not P is equivalent to non-P and Q. So in the first table, which is P, we have the values of true, false. Then the second is which is not P, we have the values of false, true. To get the values of P and P, if P is true, then not P is false, so P and P becomes true. If P is false, then not P is true, so the P and P becomes false. The fourth table, we have not P and Q. So we have false and true.
And on this problem, we are going to start from P and Q is equivalent to negation of not P and Q, the definition of NAND, and then the second problem to show that P and Q is equivalent to not P and Q and the negation of not P and Q. And now I'm going to present the truth table that shows that P and Q is equivalent to negation of not P and Q. As you can see here, we only have two variables, which is the P and Q. We also need to unpack the logical operations in the part of negation of not P and Q. Here in the table, in the column 3 and 4, which are the not P and not Q, as you have observed, if the value of P and Q are true, then when it comes in negation, we interchange it into false and vice versa. In the column 5, which is the P and Q, if both P and Q are true, then it is true. If P is true and Q is false, then it is false. If P is false and Q is true, then it is false. If both P and Q are false, then it is false. And on this part, the column of not P and Q is connected to negation of not P and Q. As what I have said earlier, that in negation, we are going to interchange the values. Therefore, if not P and Q is false, then we need to interchange it into true and vice versa. And on this part, the column of not P and Q is connected to negation of not P and Q. As what I have said earlier, that in negation, we are going to interchange the values. Therefore, if not P and Q rather is false, then we need to interchange it into true and vice versa. So if we interchange the result values of not P and Q, this will be the negation of not P and Q. If not P and Q is false, then in negation of not P and Q, this will become true. If the result values in not P and Q is true, then in negation of not P and Q, this will become false, and so on and so forth. This is Christine Joy P. Frones, and Stella Frones will continue this problem.
Thank you, Christine. And now I will continue the second problem to show you the truth table of P and Q is equivalent to non-P and Q is negation to non-P and Q. As you can see here, we only have two variables, which is P and Q. We also need to unpack the logical operation, and a part of non-P and Q is the negation to non-P and Q. In the third column of table, which is P and Q, as you have observed, if the value of P is true and Q is true, then it becomes true. If P is true and Q is false, it becomes false. And if both P and Q is false, then it becomes false. In the fifth column, the value of non-P and Q are false, true, true, and true. In the last column, which is the non-P and Q, is the negation to non-P and Q. The value of this is true, false, false, and false. Therefore, P and Q are equivalent to non-P and Q is negation to non-P and Q are congruent. This is Stella Forones.
Find a way to write PVQ which only uses the Schaeffer stroke. As you can see, the symbol V stands for the logical distinction, and this symbol T is a Schaeffer stroke. As you can see in this table, two propositions P and Q will become true, or only P will become true. Also, the Q will become true, or otherwise, they will become false. When we applied the two propositions P and Q, it yields the propositions P or Q, which denote by P, V, Q. The proposition is true when either P is true or Q is true, or both of them are true, or false as otherwise.
Thank you for watching.